So Alpha is in the business of making antimatter and studying it, making very precise measurements on the atoms of antihydrogen, which we can create here at CERN and trap in our Alpha devices. We're able to actually produce lots of antihydrogen, trap it, and then study its properties. The idea is to test if this very fundamental antimatter system has the same exact properties as hydrogen in normal matter. That's what the standard model tells us. Those two things need to be identical. So we're doing very precise measurements on antihydrogen in order to test that assumption. We have some new results, and one technique which we find is really revolutionary for our type of experiments. This has to do with a technique to cool antihydrogen down to very low temperatures. When we make the antihydrogen and hold on to it, it's already very cold. 0.5 degrees above absolute zero. All right? That's really cold. Just to be able to hold on to it, it has to be produced that cold. And that's been the main challenge to get this experiment to work over the last decade and a half. We use a kind of a magnetic bottle that holds the antihydrogen, keeps it away from normal matter in an ultra-high vacuum. That's what we call an antihydrogen trap. It's really a force field, if you will, for neutral antimatter. So we've perfected that technique. Alpha is alone in being able to do that. And in the last 5 years, we've learned how to measure things with these trapped antihydrogen atoms, predominantly using lasers. We've studied the internal structure. What we've developed now is a technique which is very common in modern physics with matter, which is called laser cooling. This uses lasers to slow the motion of individual antihydrogen atoms so that they're not bouncing around so much. Laser cooling is very, very difficult with hydrogen for lots of technical reasons, but having to do with the internal structure of the atom and the type of lasers that you're able to produce. In order to laser cool antihydrogen, our colleagues in Canada have developed a very precise pulsed laser that excites a particular transition in hydrogen or antihydrogen. It takes a lot of pulsed energy, and the wavelength of this laser is in the far ultraviolet, which means it doesn't propagate through air, it has to stay in vacuum. Technically a very, very challenging experiment to do, even with matter. We've already managed to demonstrate an effect on the spectroscopic measurement using the cold antihydrogen. We've measured a spectrum of this fundamental transition that we're always studying in antihydrogen, and it gets narrower. That means the frequency dependence is smaller. We're localizing that frequency more accurately, or we're able to in the future. The gravity measurement that we would like to do when we start up again in August of 2021 is extremely sensitive to this motion of trapped atoms. The Nature article talks about demonstrating this laser cooling, it's called, in antimatter. To do this in antimatter is a real experimental tour de force. And we think it's really a game changer for everything that we do in this building with antihydrogen.